number of consultancy papers and so on. So I'm not going too much into that. But you can give a little bit about yourself, a little briefly, sir, so that it will be helpful for the people who are listening to your talk.
All right, ma'am. Thank you, ma'am, for this brief and nice introductions. You are absolutely correct. I have already, at IIT BHU, working as a professor. I joined at IIT BHU in 2005, right, as lecturer, and since then I'm working on fuel cell. And not only fuel cell is my core research area. And apart from fuel cell, waste management, mainly plastic waste to energy, right? And through pyrolysis. Okay, there are many modes, but mainly our work is focused on pyrolysis of plastic waste and design modification of reactor, and also catalyst preparations, as well as use in the pyrolysis processes. Apart from that, we have also worked on biodiesel from some common oils like peanut, rapeseed, and mustard oil. But the problem of production of biodiesel is the raw material, the oil which are going to use as an edible oil. So you might have seen that people are talking of biodiesel, but we don't see any future because of raw material crisis. If you use non-edible oil like palm oil and all, it's okay, all right. But palm oil, other non-edible oil, they have high free fatty acid. So high free fatty acid have other disadvantages or demerits when we prepare biodiesel. So in that sense, biodiesel, I don't think it can compete with other energy materials like if you say renewable energy, like solar, then wind, etc. But fuel cell as another class of energy generations, energy producing device that converts hydrogen rich fuel to electricity via electrochemical reaction. So I have also have a expertise more than a decades on fuel cell, mainly to produce electricity directly by feeding hydrogen, as well as ethanol or methanol, that is basically hydrogen rich molecule in a fuel cell, using a suitable catalyst. Basically electrodes are in fuel cell is basically catalyst, right? And that catalyst play catalytic role and split the fuel at electrodes, basically anode side, and then produce hydrogen ion and electron if it is a acidic medium. And for alkaline medium, of course, OH ion will be produced at cathode side. So the main challenges of fuel cells are basically the material cost. So it is very expensive. Most of the materials are procured from abroad, and that's why manufacturing means fabrication cost is very high for fuel cell. So unit cost of electricity via fuel cell will be very high. So therefore we are working on material synthesis for fuel cell as well, like catalyst synthesis, membrane, that is the membrane electrolyte, it's the heart of the cell, which acts as electrolyte, and that is also very expensive, because Nafion is the membrane used in fuel cell. Okay, all of you know this DuPont as the proprietary, it's the proprietary product of DuPont. So if we can replace this membrane with some alternative, then we can reduce the cost. So if you can manufacture catalyst in our own, we can reduce the cost. So this way we are trying to synthesis material in our own, in our laboratory at IIT BHU, to reduce the cost of fuel cell. So last but not the least, the topic which I have selected, that is pyrolysis of plastic waste. And people are working at a large extent on pyrolysis of plastic waste. So what are the novelty? What are the specialties are there in our work that I shall discuss in detail. Okay, and before I go to my topic, I would like to request give me permission to share my slide, ma'am. because I have a PPT, so I have no sharing. Yeah, thank you, ma'am.
I'm sorry, I thought I had made you present.
No, ma'am. It was, now it is activated. So, all right, ma'am. I hope my screen is visible.
Is it possible to make it full screen, sir?
Yeah, ma'am. Yeah. I'm doing that. Right. I hope my screen is visible, ma'am. Is it my visible, ma'am? My PPT?
Yes, yes, it's visible, sir. It's visible.
Okay. So before I start my lecture, I'd like to thank Professor Lima Rose Miranda, ma'am, for giving me this opportunity to deliver this lecture in this faculty development program on this topic, material and techniques for the treatment of waste. And I have selected this topic keeping in mind the theme of this FDP program, that waste management. So I thought waste to energy would be a good choice. Basically, waste here is a plastic waste. So topic of my presentation is a novel approach of solid waste to energy recovery via in situ aromatization and pyrolysis of plastic waste. So, when you are talking of waste management, there are many options. There are various types of waste generated, either domestic or industry, right? And domestic waste, basically, it is considered as a finally municipal solid waste. And industry also counts a lot, and all these waste basically pollutes either air, water, or land in various means based on their nature of the nature of the waste. Now all this waste material management is really it's a very problematic. Now if you can manage waste to produce energy, right, then it will be a very much beneficial for us to save the one side, reducing the waste to environment, waste load to environment, as well as producing energy. And there are many people are working on waste management, like for water pollution, wastewater treatment, but they are treating the waste to get the pure drinking water. Similarly, people are working on air purification, like SOx NOx removal, which is coming out from thermal power plant, to reduce the air pollution, to remove the pollutants, like that I already have told you, that causes health issues, as well as degrades our environment. But solid waste is also a big problem for us. And if this based on the solid waste, if we segregate this, and the hydrogen or the solid waste which contain the hydrocarbons, carbon and hydrogen in this form, so we can conveniently convert them to valuable products. So in view of this, I have integrated this, these two techniques, waste conversion to energy for the production of energy. So we are minimizing waste load to environment and producing energy, right? So what are the various sectors we need energy? There are four major sectors we know where we need energy. Uh, Domestic or offices, one segments, industry, transportation, and military. In each and every sectors, if you see, either heat in the form of heat energy, or that is thermal energy, or electrical energy. In these two mode, we need the energy. So heat energy or thermal energy is basically derived from renewable or non-renewable sources. So non-renewable basically, fossil fuels that we know, coal, petroleum, or natural gas. Or if you talk about renewable, solar or biomass in the form of heat, solar thermal energy, there is a solar flat plate collectors, there is a solar heater which you are used to trap the solar thermal energy. Similarly, biomass, this renewable form, we can have energy from from biomass after combustion. So this are the renewable and non-renewable sources through which we can have heat energy. Other form is electrical. Again, non-renewable and renewable nature. Non-renewable, if you say, is a fossil fuel-based thermal power plant. All this fossil fuel that produces heat, that can be again converted to thermal power after generation of steam. Okay, that heat which is produced from combustion, that can be converted to steam, and then steam will give you thermal power. And another is battery technology, that is lithium ion battery, nickel cadmium battery, chargeable battery, rechargeable battery, that is secondary battery. So these are basically non-renewable nature, because you have to recharge it to get back the electricity from this battery. But renewable in nature is solar photovoltaic, electrical energy. If you want to have in renewable route, then SPVs are there, then wind energy, hydropower, right? And another is category is fuel cell. That also is considered as a renewable, because hydrogen, if it is produced via electrolysis of water, that hydrogen is a production is a renewable route, or it is called renewable hydrogen. That renewable hydrogen can be used in a fuel cell. So energy production through such route using a fuel cell is also considered as a renewable in nature. Now if you see the overall scenario, 70% still the energy production share is through non-renewable, and renewable only 30% share. So non-renewable is a percentage is very high. So that comes due to the fossil fuel mostly. And as we know, fossil fuels are having many problems: limited storage, combustion of fossil fuel will give you pollutants, emission of pollutants, greenhouse gases. So renewable energy as such have no problem. Of course, there is, if you talk about hydro, there is some impact on our ecosystem. But if we take precaution, then we can minimize those damages to the ecosystem. Now in view of this, if you say that energy share, that 70-30%, 70% non-renewable and 30% renewable, so to reduce this dependency on non-renewable resources or conventional energy resources, so devising a sustainable energy resources are very essential, which is environmental friendly, cost competitive with fossil fuel, and to devise that such sustainable technology is really a big challenge to in the 21st century. We are talking of many research on these renewable energy sectors like solar photovoltaic. Solar photovoltaic nowadays, due to the initiatives of government, almost it has increased the use of solar photovoltaic in a higher side. And the problem is with the cost. The government is giving subsidy. It's not that solar panel cost is low nowadays, that's why cost is low. Government is giving subsidy to promote solar photovoltaic. So if you can produce the SPV in our own, PN junction or material for SPV in our own, then cost will be reduced. Okay, so that's why the cost must be low. By giving subsidy, reducing cost, it's not a solution. The material cost has to be low, and of course the environmental friendly. Now, as already I have said, that the main major problem of non-renewable or conventional energy resources is the pollution problem. Therefore, these are the key reasons to work on energy to produce this low cost energy from a waste material. So if you can produce energy from waste material, so one side we can reduce the waste load to the environment, as well as we can trap or derive energy from those material, so we can save fossil fuel as well. Therefore, what we can say, a futuristic view of energy supply will be based on hydrogen economy rather than fossil fuel. So we are switching over from purely fossil fuel to the hydrogen energy, and shifting to hydrogen economy can reduce the use of fossil fuel and greenhouse emission. So a key technology to enabling a hydrogen economy. What is hydrogen economy? Hydrogen economy is using of hydrogen, or hydrogen gas or hydrogen fuel, right, in place of fossil fuel. Okay, so key technology that can enable the use of hydrogen economy is a pyrolysis of waste plastic. That is, this is my submission or recommendation. There are many other techniques maybe to enable the hydrogen economy, but pyrolysis could be an option. Pyrolysis of waste plastic to encourage or to add up to the hydrogen economy. Now, as I have said, the plastic waste to energy recovery. So what is plastic basically? Plastics are synthetic organic polymers of high molecular mass synthesized by polymerization of petrochemicals, right? So from petrochemicals, from various monomers, hydrocarbon, basically we produce by polymerization. Different types of techniques are there, polymerization techniques are there. I'm not going in detail of that. We produce plastic, and different types of plastics they are in practice. What are those? Polyethylene, polypropylene, polystyrene, polyvinyl chloride, polyethylene terephthalate, PET bottle, PET bottle, okay, polycarbonate. All these materials have their own use, and they are in large practice for the manufacturing of different types of usable material. So we cannot think our life without this plastic material. And these are the different code which basically designate different types of plastic. One means PET, polyethylene terephthalate PET bottle, that mineral water, or there are many other liquid which is used for packaging of these liquid products. The PET bottle, PET bottle also we say. One means if it is not mentioned, even we know it is a PET bottle. And if it is, let's say 4, then LDP, 3 means PVC, 2 HDP. So this way these are the numbers which designate different types of plastic material. Without knowing the plastic material from which it is being manufactured, just simply from the number we can identify the raw material. The reason behind the use of plastic, first of all, no doubt, the lightweight, of course, durability, faster rate of production, design flexibility, and low cost. These are the major reasons. All these, 5 reasons, key reasons are there. That's why we have, this plastic is very much popular. However, these plastics have many demerits. Non-biodegradable, and already I have told, it pollutes water, air, and soil, right? And this, of course, damage our environment. If you talk about, polystyrene, that is basically thermocol polystyrene. It is a monomer of, it is manufactured from a monomer of styrene, and thermocol, it is used for cutlery, this teacup, as well as plates as well. So these are basically thrown after use in the with a municipality solid waste, and then we have seen many times it floats on the water body, not only pond, you can see in lakes as well as in the seas also. It is found, it is floating on the water body, and that pollutes the solid land and as well as water. Therefore, there is a need for developing some sustainable method which could reduce this plastic waste or alter some value added products like light paraffin of diesel and kerosene range. I have concentrated in these two products, right? Selectively, the process is such that we can have our target molecules and we can get the desired specification as needed for the diesel, similar to diesel. So diesel and kerosene have some, they have certain specification as needed in the diesel engine, or for kerosene as the illuminants. So these properties are also achieved through the pyrolysis and aromatization. So this process, not only pyrolysis, also aromatization and in situ aromatization we are going to use. The benzene, toluene, ethyl benzene and xylene are valuable products which could be produced from waste plastic by the pyrolysis process. So people are basically, scientists are working on simply thermal decomposition. If you heat the plastics waste in absence of oxygen at a certain temperature, let's say above 500, then it will be decomposed and give you monomer, because it is a from monomer it was polymerized and we obtained the this plastics polymer. Now again we can break down into smaller fragments, but if you simply supply heat and do the thermal pyrolysis in absence of oxygen, it will give you random product distribution. You cannot have diesel and kerosene like fuel oil, or benzene, toluene, ethyl benzene, xylene like aromatics, because these are the valuable hydrocarbon, aromatic hydrocarbon. That's why I have added this term, pyrolysis and aromatization. Benzene, toluene, ethyl benzene and xylene, these will be produced. Even if you analyze the fuel oil like gasoline as well as diesel, what we observe that benzene content is as low as possible. Why? Because benzene is it has a soot forming properties, but toluene, ethyl benzene and xylene, they are considered as a good fuel component. For gasoline, it improves the octane number, right? So that's why what we thought, why not we concentrate in conversion of pyrolysis products in situ aromatization in the same process, right? By certain arrangements of internal arrangements or modification of the reactor to convert pyrolysis product to these valuable aromatics like benzene, toluene, ethyl benzene and xylene. What are the uses of these four major aromatic hydrocarbon? Benzene used for styrene manufacturing, phenol, cyclohexane, nylon precursor. Gasoline blending for improvement of octane number that I told you. To manufacture, ethyl benzene is used to manufacture styrene, which is then used for polystyrene manufacturing. As a solvent also, and in gasoline it is used, to improve the octane number. Not only toluene, ethyl benzene is also used. Xylene, it is used in production of plastic bottles, polyester clothing, then as a solvent with a range of application for circuit board cleaning and varnishes, etc. Means xylene as a solvent, right? Major as a use as a solvent. Now, if you see the current status of plastic waste disposal in our country, right? Though this data is of 2013, but still we can see and that this figure has gone up, right? Tremendously. If you look at the present data, though I don't have now, but if you see 2013 data, even CPCB report, 5.6 million tons of per annum plastic waste is generated, right? And 10% only recycle, only 10% mean 10% is recycle, remaining is used for landfilling and incineration. And among these two, incineration and landfilling, around 69-70% used for landfilling, and then incineration 10 to 12%. So if you see that landfilling is used for major amounts, right? In our country, we don't have good management system to convert or to recycle it or to convert it into valuable products. I'm talking of plastic waste. So if you see the waste, total waste, about 8 to 15%, right? It is basically plastic. So plastic waste contributes around 8 to 15% among solid waste, right? Government of India 1997 data. So that may be little higher side, around 20%, right? Though I have not reported here at present data what it is saying. So if you see that plastic waste generation is always higher than the recovery. So plastic waste recovery and this, there is a huge gap between generation and, recovery. So that's why there will be accumulation, of course, right? If you do not recover the plastic and reuse or recycle it or reconvert it into some valuable products, so there will be a dumping or plastic load will increase in the environment. Different cities means four major metropolitan cities. If you look into it, you will see Delhi. It produces maximum amount of plastic waste, 689, 690 around tons per day. It's a huge amount. Then Mumbai, Kolkata, and then Chennai. Among these four cities, Delhi is highest. Okay, and if you see the uncollected or littered plastic that is not collected or recycled or reused, there's a huge amount. So 275 tons per day it is, littered or uncollected. So that's why you can see there is a huge gap, plastic waste generation and as well as, in reusing. Now, I would like to give you data of Varanasi city. We are talking of countries perspective and all. Four major cities we have seen. Now, as I am from Varanasi and at IIT BHU Varanasi, I am much more concerned for the, our city. We talk about world scenario, talk about country scenario, but we should know about our, local place as well, where we are residing. What is the status? So Varanasi city, if you look into it, food waste means municipality solid waste. I am talking, this 32% food waste, 32%, and plastic waste 22%. I am not going to other, type of waste like cardboard, glass, paper, textile, leather, metal, etc. But these are two major. So food waste, organic mass is, biodegradable. Food waste is biodegradable, 32%, but 22% is plastic waste, which is non-biodegradable. Apart from within this 22%, if you analyze, you can see that polyethylene is around 41%, which is very, very high amount, right? In comparison to other plastic that I discussed earlier as well, that polyethylene, polypropylene, polystyrene, right? PET, PET bottle, okay? So highest is polyethylene. And you can we cannot imagine nowadays without a plastic means polyethylene. If you go for shopping or for buying vegetables, for groceries as well, the shopkeeper will give you plastic for as a carry bag. Okay, there were a lot of efforts being made to replace or to eliminate the use of plastic waste, but we are not successful. And time to time we have seen that ban is imposed on use of plastic waste, mainly polyethylene, right? But again we have seen that people start using plastic. So what I understand, that we have to stop at the production level rather than at the user end. So we ask user to stop using this plastic. We do not stop at the production level. So that I think we know why we do not go into that level, that do not don't produce plastic, then nobody will use. Means if I have an option to there are two options, textile, one carry bag of jute, as another is plastic. So plastic carry bag will cost around 50 paisa, right? Even not 1 rupees. So even you can have a 4 plastic carry bag of standard size in 1 rupees, but one jute or carry bag of made of textile, that is a biodegradable nature, environmental friendly, and that is cost around maybe 5 to 10 rupees. So this is the problem nowadays. In shopping mall we have seen that this type of textile or this jute bags are given or made of paper, okay, which is biodegradable, that they charge us either 2 rupees or 5 rupees for each carry bag. Okay, so That's why if you see the cost, if you compare, the cost is low for the polyethylene and in comparison to textile and this fabric bags. So if you want to clean our environment, then of course we have to pay for it. Otherwise, this pollution problem we cannot reduce. So although we are talking of conversion of plastic waste to energy, but it's very difficult to convert all plastic waste to energy material. And I shall discuss what are the plastic type of plastic we can convert. All plastics types that I have said, that polyethylene, polypropylene, polystyrene, PET, okay, PVC, all those you cannot convert. Only 3-4 types you can convert easily. Rest you cannot do because of there are some limitations. Now, municipality solid waste of Varanasi, if you say tons per day basis, 800 tons per day plastic is produced. It's huge amount, and per capita 200 grams per person per day in Varanasi, huge amount again. 200 grams of plastic generations. The statistics shows that major amount of plastic waste consisting of polyethylene, polypropylene, polystyrene and PET. So that's why we concentrated on those 4 types. But again, we did some literature whether those plastics are possible to convert or not. So I shall discuss next slide. Now think on mountain area. I have talked about national scenario, then Varanasi. Now if you look at high altitude mountains area, that those areas are not also deprived. Those are also greatly affected, right? Mountains area and or cities are very major cities of India at high altitude. The plastic bottles are thrown by the tourists, local resident and military people. However, no such studies on those plastic waste generation at high altitude have never been reported, okay, or found in open literature. Only some articles in 2018 was published, like in this headline, using this headline, a Himalayan mesh growing garbage file a threat to mountain ecosystem. And this information, if you say that World Environmental Day, Environment Day on 5th June, volunteers of 200 organization picked 4 lakh pieces of plastic waste in a 2-hour of operation from Himalayan states of Sikkim, Meghalaya, Tripura, from north to north east, this region. If you see all the states, okay, 4 lakh pieces, huge amount, right? So, tourists, local resident and military people, they are the major threat, means they don't take care of this, plastic waste properly disposal. Okay, they throw here and there. Most of the plastics are cups, chocolate wrappers, juice, chips packets, Tetra packs, etc. So here also, PE, PP, and polystyrene are found. So not only in major metropolitan cities of India, also Himalayan areas are greatly affected. Okay. So plastic waste management techniques, if you see methods, landfilling, I already have told you, that's very high amount, 79%, 12% incineration, and 9% recycle. So major amount is landfilling, and that are having many problems, requires large space, non-biodegradable in nature, pollutes water and soil. Energy content in the plastic we cannot recover after disposal. And last points is very scary, basic, because cow and dogs are often seen to scavenging garbage dump, which is harmful to animal. And many times we have seen the cow, they die due to this consumption of plastic with some food stuff, right? So that's why landfilling we have to reduce as much as possible using this plastic waste. Now incineration also have some problems. It is a combustion. Incineration is nothing but combustion. It produces toxic fumes, polyaromatic hydrocarbon, polycyclic aromatic hydrocarbon, dioxins, and it accelerates global warming. Next, recycle. Recycling is the most effective way to deal with this plastic waste. However, we are facing this problem of recycle due to lack of awareness. You know, in India also we have started, but in abroad people follow this stringent specification or guidelines. There are different color code, and based on the color code they dump the particular plastic in that particular, you know, dustbin, like blue for paper, green for plastic, glass, red, and then general items or stuffs, waste stuffs in the yellow one. So that is the lack of awareness. That's why we all together put in a carry bag again plastic and throw in a dustbin, or municipality that you know that people, when they come, we hand over them with again this carry bag. So you know, there is a bean bag also made of plastic we use nowadays, that also creates a pollution. Now many plastic can be recycled and materials can be recovered and given a second life after, you know, recycle. This method is not fully utilized due to difficulties with the collection, sorting of plastic waste that I told. In India, we all mix together in the, you know, with the municipality solid waste is go to the, you know, dumping zone. If you want to collect all those plastic, we have to have a good system of segregation to recover and then recycle it, or to use it for some other conversion techniques. Now, out of the apart from three techniques, recently pyrolysis has also gained attention, as it can convert this means plastic waste can be converted to valuable products that I have told you by thermal decomposition method, right? Now, if you talk about you know, pyrolysis, it is a thermochemical decomposition of material at elevated temperature in the presence of in the absence of oxygen, right? And it involves the simultaneous change of chemical composition and physical state as well. There are two types of pyrolysis process. One is thermal process and another is chemical process, catalytic pyrolysis process. Thermal pyrolysis process needs high energy, right? This needs high energy, high temperature it requires, and impurities remains in the fuel. It is non-selective process. It gives random product distribution. You do not know after pyrolysis of, let's say, plastic, what type of products you are going to have. If you change the temperature a little bit, the product will change, right? Different types of product you can have. Means when you talk about the liquid oil of pyrolysis, that will consist of a multi-component. There may be a, you know, linear chain hydrocarbon of liquid range, alkane or paraffin. There may be a naphthalene. There may be aromatic as well. So there may be different types of, you know, their isomers as well. So these are, that's why thermal pyrolysis will give you all sort of hydrocarbons of their the various range, right? So if you want to have a selective products, let's say I want a paraffin of short chain, or aromatics of lower molecular weight, not higher aromatic hydrocarbon. Higher aromatic are having problem of, you know, soot formation, right? They gives a carbon soot, or you know, that is known as a carbon residue. Finally, that deposits in the engine if it remains in the diesel oil, and problems creates a problem in the combustion of IC engine based on diesel. Okay, and efficiency of the engine, as well as if you say the fuel efficiency will go down. So thermal pyrolysis, in that sense, it's not good over, you know, not considered as a good choice. So liquid fuel produce high liquid yield and heavy oil. It is a heavy oil, contains impurities and low octane number. It's a non-selective. Gaseous produce less quantity and contains CO2 in high concentration if there is a oxygenated species in the, you know, in the raw material. Char is produced in high quantity, right, at low temperature. Catalytic process demand less energy, demand less temperature. So at low temperature, we can convert the plastic waste to valuable products, okay, and of a good quality. So decrease the yield, decrease the liquid yield. Yield will be low, liquid yield, but quality will be better. low quantity but high quality of fuel you can have, of gasoline range with high octane number. Increases the production of gases because it is, you know, catalytic process. So more and more, you know, smaller fragments will be produced, like C3 to C4, propane, butane, methane as well. Okay, decreases the char quantity, char is having a high surface area, and that can be used as an adsorbent for water purification process. So polyethylene, if you see, as I have told that three major plastics are found: polyethylene, polypropylene, and polystyrene. So this is the structure, chemical formula, and the structural view. And if you see the products, which are from the from the raw material of polyethylene, basically plastic bags, plastic films, geomembranes, containers including bottle, etc. Similarly, this is polyethylene structure. If you see the stationeries, textile, labeling, packaging, and reusable containers, etc., they are produced from polypropylene. And these are, there's some properties of polypropylene, just like polyethylene. Next is polystyrene structure I have shown here. And if you see disposable glass, plate, packaging, plastic model assembly kits, and many other objects where a rigid and economical plastic is desired, this polystyrene is used. And mostly you have seen, if you have a heavy, delicate items being transported from one location to another, we have seen using a thermocol. Whereas the electronic item or any delicate item is being transferred, so a large amount, large volume of plastic, this polystyrene, is used for packaging, and that go to the environment if you do not recycle it or reuse it or convert it into suitable products. What are the mechanism of polymer decomposition? So when you talk about pyrolysis, so pyrolysis follow this, four steps. First is chain initiation reaction. So if you have a polymer, then there will be cleavage of bond and forms the radical. This part is shows that dot means it is forming a radicals, right? So this is radical forming from polymer, random scission. Next is chain propagation reaction. Propagation reaction, first step is the depolymerization through beta scission, which will give you this, this radical what I have shown here. So this radical will be converted to smaller radical as well as some other compounds. Okay, some unsaturated hydrocarbon, and with some, this radical. Here you can see this radical, and also another route giving also radical with some, unsaturated hydrocarbon. Intramolecular hydrogen transfer reaction. Intramolecular hydrogen transfer within the same molecules. This radical you can see from this position, it has been transferred to here, and hydrogen atom been transferred to other, carbon atoms. So this way intramolecular hydrogen transfer takes place. Intermolecular, two radical will rearrange, and then there is a hydrogen, transfer will take place. If you can see CH2, it has become CH3. So one hydrogen has been transferred to from second one to the first one. So this way intermolecular hydrogen transfer takes place. Next is chain termination. So two radicals, if there are two radicals, then they will form a, another compound that will terminate the chain. Radical will give you this final form of compounds that answer different radicals and different reaction being shown here. All right, I am not going in detail of that. And for aromatization, what happens if you have an alkane? Proteolysis will take place, and then carbonium ion. Carbonium ion, there are two paths. First cyclization, then dehydrogenation. Cyclization will give you naphthalene saturated ring structure. That is, if you say benzene-like structure but saturated, there is no unsaturated bond, so it is a cyclohexane. And if you say dehydrogenation, minus hydrogen, right? Hydrogen will be dehydrogenated, and then it will give you aromatics like hydrocarbon. Okay, I am giving you example of benzene. or beta session from carbonium ion will give you alkane or alkene, that is unsaturated hydrocarbon, right? Next is uh, the selection of plastic. We should know what is the basis when whether you can go for pyrolysis or not. Just we look into it. Polystyrene, good for pyrolysis process. Low temperature required, produces less viscous oil compared to polypropylene and polyethylene. This polystyrene I am talking. This is the literature source we have taken. Polypropylene also good for pyrolysis and required little higher temperature, right? And thermal pyrolysis give waxy product, right? But we can manage using catalytic pyrolysis, right? We can have a good quality of oil. Then polypropylene also, it's a good for pyrolysis. And now polyethylene terephthalate, that is PET, if you look into it, they're not suitable. Why? It produces benzoic acid. So benzoic acid is solidifies at the neck or condenser line, which choke the vapor path or vapor lines, and it's not it is very dangerous, right? So safety point of view, it's not recommended for pyrolysis process directly. Only after design modification it could be done. So polyethylene terephthalate, it give benzoic acid, that's why it is not recommended. Polyvinyl chloride, it produces chlorine vapor. Again, it is not recommended due to the escape of chlorine in the environment. So based on literature, as I've said, that polyethylene, polypropylene, polystyrene were chosen for pyrolysis and followed by aromatization, in situ aromatization, to produce diesel range liquid hydrocarbon, along with some major aromatics like benzene, toluene, ethyl benzene, and xylene. So these are the few literatures. If you see here, for thermal pyrolysis mainly, it is for thermal pyrolysis. So I have highlighted with green color just to show here that polyethylene, LDP, polystyrene, and polypropylene. What is their output? As a liquid product, 93%, 97%, and 92%. More than 90% in each cases we can have with a little amount gas and very small amount solid residue. This is for thermal pyrolysis of this three type of plastic waste. Similarly, catalytic pyrolysis, if it is from the literature survey, it is seen that LDP, low density polyethylene, it gives 93%, right? Pyrolysis temperature is 450, and then polypropylene, right, 330 to 450, and polystyrene, it is 400 the degree Celsius. All these are in degree Celsius we are talking here. And here you can see liquid also 93%, 15 to 18% for polypropylene. In this range is given here, whatever it is available in the literature, and 96% liquid oil is obtained. But here this paper, it is they have not shown the qualitative analysis. That means in terms of benzene, toluene, ethyl benzene, and other hydrocarbons like paraffinic hydrocarbons, naphthenic hydrocarbon, naphthenes, not shown. So only quantitative analysis given here. Now from this overall literature survey, what we observe that there is a good possibilities of research on conversion of plastic waste to aromatic hydrocarbon, benzene, toluene, ethyl benzene, and xylene, which rich fuel which is suitable for generator set, because all those hydrocarbon aromatic hydrocarbon when remains in the oil, that means we say it is good for diesel engine, right? But I have already said benzene percentage is little bit high, so that percentage we have to reduce either by some separation process or some by means of some conversion technique, after conversion benzene to toluene more using some suitable catalyst or reactor bed arrangements. Second thing, no detailed study on reactor design, okay, process parameter study and product composition analysis of fuel oil obtained from plastic waste has never been shown, has not shown yet, right? In terms of reactor design. So third one is there are many natural catalysts. JDSM-5 is the widely used commercial catalyst, but apart from JDSM catalyst, there are many natural material which could be recommended as a catalyst for pyrolysis or aromatization. So therefore, to produce low paraffinic fuel and BTEX from waste plastic, two major areas are considered in this study. One is reactor design and catalyst arrangement, reactor design and catalyst arrangements, and second one is catalyst type. So by doing modification of changes in design of design and catalyst based arrangements, we observe a huge enhancement in the BTX content in the oil as well as quality of the oil. And catalyst also we tested, not only commercial, also some natural material we selected. I will discuss in the next slide, next to next slide in the experimental section. So what is the objectives? So for each study research, there must have objectives based on the gap we found from the literature and based on our goal, specific goal, design and fabrication of setup, and then study both the pyrolysis thermal and catalytic for comparison purpose. If you don't have a thermal pyrolysis data, then you cannot compare what is the enhancement in yield as well as quality of in terms of BTEX. Then product characterizations using the various techniques, standard techniques, GCFID, ASTM distillation, flash fire point, calorific value, and carbon residue. Okay, these tests are also recommended for diesel oil or gasoline to know and compare with the standard data, whether it is a standard fuel or there is some mixing or the impurities or adulteration is there or not. Two major raw materials was used here, and that is one is plastic, of course, and second one is catalyst. Plastic, polyethylene already I have told, and preparation technique. What is the preparation of feed raw material here? Collection, washing, drying, and shredding for pyrolysis and catalyst used was JDSM-5 and fly ash synthesized catalyst or red mud and river clay. I shall discuss only fly ash here because of time constraint, and as well as JDSM-5. JDSM-5 is a JDSM is full form is Geolite, Soconi, Mobile. Okay, these three scientists they developed it, and this is the structure and formula of this JDSM-5. And sodium, basically JDSM-5 means Na-JDSM, sodium JDSM. It is a sodium JDSM form. You can see Na is there, right? In zeolite structure, it's a pentacyl structure. And nowadays, JDSM-5 is being modified with ammonium chloride to protonate it, protolysis after protolysis, which is known as a HJDSM. So Na is being replaced with ammonium chloride in the form of NH4, okay, which is known as a HJDSM-5 to have better aromatization and to have a better alkylation and more selective products, target molecules in the process. So JDSM-5, what we selected here is a fixed ratio, because with the changing of silica to alumina ratio, acidity basically changes. More the silica aluminum, the acidity is increased basically. So this is also considered as important parameters, the silica alumina ratio. Now for fly ash material, as we selected as a raw material, means for catalyst synthesis or silica alumina synthesis from fly ash, because 184 million tons per annum fly ash is produced from the thermal power plant in the data of 2014-15 data, it shows 184 million tons, huge amount fly ash, okay, produced in 2014-15 is an Indian scenario. And maximum fly ash generation in Uttar Pradesh, you see 24.37 million tons per annum. Okay, this data, I am giving the data, these references, these are the references taken. And keeping in view of this, what we did, fly as a Panki thermal power plant. Panki thermal power plant is nearby area of Varanasi. We got collected fly ash, and if you see the composition of raw fly ash, then silica is highest amount 53.56. 27.71, it's a second highest amount of this active constituents. Then Fe2O3, it is also considered as a good catalyst. Magnesium, MgO, these are the four constituents which acts as a good catalytic, play good catalytic role. But first two, silica alumina, as you have seen in zeolite, there is a silica alumina. So we considered silica alumina mainly to use it as a active components for the catalytic conversion. How we finally prepared the catalyst from the fly ash. These are the steps, major steps. Sample fly ash was water washed to remove the dirt and soil etc. from it. Then it was dried, then screened after drying, and then calcined at various temperature, let's say 600, then 700, then 800 and 900. Four different temperature we selected, and uncalcined catalyst also was there to compare if you have a four different types of catalyst after calcination, and if you have uncalcined, what will be the change if you for better comparison, rather you can see among the products which is obtained using these four calcined catalyst and uncalcined fifth one. And they were designated as a Fa600 for 600 temperature when it was calcined, then Fa700 for 700 degrees Celsius when it was calcined. Similarly, 800, Fa800, Fa800 and Fa900 for 900 degrees Celsius when it was calcined. This calcined designation is very, very important. Otherwise, it will be very difficult to compare and explain the process. And FAN means natural catalyst. FAN, fly ash natural catalyst. What are the characterization techniques? So both oil, product oil and the catalyst were characterized. So catalyst characterization was done by XRD, same EDAX analysis, BT surface area and FTIR. This analysis basically says about the crystallinity, right, for various active components present in the fly ash. Same EDAX, it gives the informations about the elemental composition, but surface elemental composition, whether silica, alumina, active constituents in elemental, how much what is the weight percent present at the surface level, it gives the informations. BT surface area, it gives about the surface area, right, meter square per gram, okay, BT surface area. And from this we can interpret this physical characterization data with the products. It is presumed that if surface area is high, it is expected to give a better product in terms of as there is a better interaction in terms of liquid or quality. Of course, catalytic pyrolysis will give you low liquid, little lower yield, liquid yield, but quality wise it is best quality for catalytic. Similarly, if you talk about gas, gas will be high for the catalytic pyrolysis. So higher the surface area, higher will be the interaction with the polymer first, and then after degradation of the polymer, then little larger fragments will be formed. Those larger fragments will interact with the catalyst, and then it will give us smaller fragments, and various routes will give you various types of product distribution. But our concern, more the surface area means more will be the interaction, more will be the product formation and target molecule we can achieve. Product analysis, these are the various methods for product analysis. Yes. May I continue? Is there any question? May I proceed? Okay. So product analysis are done through FTIR, GCFID, GCMS analysis, then carbon residue. FTIR of course will tell you about the functional group. GCFID also will tell you about particular species. If it is a multi-component mixture, there is a retention time and peak area. From this we can find out what are the species are found. If you know the reference molecules data you have from those retention time of reference molecules or species, you can compare of unknown species and you can say this is what are the species form. And GCMS of course will give you the exact information about the particular species. Okay. Carbon residue, it talks about what are whether there is a higher the possibility of having higher aromatic hydrocarbons in the product oil. If carbon residue is more than 1%, then product is not recommended for IC engine, mainly diesel engine use. Otherwise it will create a carbon deposition problem and engine will stop running after few months or after few years. So because of the carbon deposition, when carbon residue will be high, I told you, if aromatic content higher aromatic, let's say one benzene ring with long chain hydrocarbons we are having. So long chain hydrocarbons will break down the straight chain paraffins with benzene. So straight chain paraffins will broken down fast, and then with some free radical it will form. So this free radical might attach with another free radical which is at integrated part of benzene. So this way benzene ring, this way it will form a giant molecular structure, and that will appear as a carbon residue. So remember, carbon residue, that this what I am talking now, it's not a pure carbon. It is basically polyaromatic hydrocarbon, giant molecular structure, right? And that deposits in the engine and creates in the problem if those type of aromatics are present. But BTEX, what I am talking, that won't create so much problem except benzene. So benzene is not recommended, and if you analyze the fuel, you can see less than 1% benzene is there in the, whether it is a gasoline fuel or it is a kerosene or diesel. I will show you during my product analysis and all. Similarly, flash and fire point. Flash point is the temperature at which with the introduction of the spark or flame, the flash, momentarily flash we get, right? When fuel is burned, fuel is heated in a standard apparatus, ASTM apparatus. All these are done. I am telling you, this carbon residue, flash and fire, ASTM, API gravity, or gross calorific value measurement in using some standard. This may be ASTM standard, American Society for Testing Material, or IP standard, or it may be Indian standard, IS standard. IP stands for Institute of Petroleum. So if you give the code like ASTM D86, D86, it has a standard protocol for ASTM distillation. So no need to discuss the method, just give the code so it is understood. So flash point means momentarily flash will occur. Then above this flash point, just by 3 to 4 degree beyond this more temperature, the if you keep on increasing the temperature beyond this flash point, just after 3 to 4 degrees Celsius, what happens with the introduction of spark or fire or flame, the fuel will start burning continuously. So when there is a continuously burning combustion of the fuel, then we say fire point. So if you, let's say, fire point is 40 degrees Celsius, so 43 to 45 degrees Celsius would be the fire point. It's the thumb rule, but we must test the fuel to know the exact flash and fire point. And it says about the fire hazards tendency or of the fuel for safety point of view or handling or storage. So if you do not know these points, flash and fire points, then we may face some fire hazards problem when this fuel is either stored during storage. Suppose temperature is around 50 degree in Jaipur, right, during summer, but its flash point is 40 degrees Celsius. I hope you understand the temperature of oil is higher than 10 degree high than the flash point. If there is this little bit spark, right, what will happen? It will explode. It will catches fire and explode. So this is a storage, for storage of oil. We should know this value. Similarly, for during handling or handling means from when we fill the tank, if the temperature is very high, again there may be fire accident. And during use as well in the engine, if flash and fire point, it gives a very important information. Lower the flash point, what will happen? The fuel will catches fire easily. That means startup will be easy. If the flash point is very high, then startup problem might be there. Flash point becomes low when the lower molecular hydrocarbons are more and more in the fuel, right? Then only flash point will be low and it catches fire easily. And one information I'd like to give you here, you should know it, that the gasoline fuel, sometimes it is blended with butane. Why? So that butane is lighter. It is a gaseous form, right? In normal temperature, it is a gas. That's why when we use this gasoline fuel in gasoline engine, means IC engine, basically it is a spark plug engine, and diesel engine is a basically compression engine, compression type. Fuel is adiabatically compressed, temperature is raised in such a point. For diesel engine, diesel basically start auto ignition. It's a self ignition temperature reaches and ignites. But in case of gasoline fuel, you have to have low flash point, so that after sparking using a spark plug, there is a positive and negative terminal, and we start basically the startup button. If you say scooter, okay, there's a self start, we say, means we just switch on, there will be a sparking, positive and negative terminal, and then what will happen? Catches fire. But high flash point means it may not catch fire. That's why butane is blended, and the butane is it is a component of LPG, right? So this is very important parameters or properties you should know of a fuel. ASTM distillation also, it gives the idea about whether what is the initial boiling point and final boiling point, and 10% distillate temperature. It's a curve between percentage distillate and corresponding temperature. And percentage distillate we collect at a certain temperature, and that percentage you obtain, that temperature is fixed. Let's say 10% distillate temperature is 70 degree. Okay, the 10% distillate temperature is 70 degree for gasoline. So for standard gasoline, if you get temperature either lower or higher, then you can say there is, it's not a standard fuel. So distillation will ASTM distillation will give you many information, and 30 to 60% in this range, this distillate will tell you about the during steady driving, you should have this percentage distillate and this corresponding temperature range. Otherwise, you cannot have a steady driving, right, of an engine. Similarly, beyond 90% also, there is a certain temperature, and those temperature range and percentage distillate must satisfy to have the better performance or standard performance of the engine using this standard fuel of gasoline, or it may be diesel, or it may be any sort of fuel, aviation turbine fuel or jet fuel, etc. API gravity, it also says about the oil, whether it is a heavy oil or light oil, or medium oil, medium type oil. Now there is the equation. API stands for American Petroleum Institute, right? API, American Petroleum Institutions, they have developed a correlation that is 141.1 by rho minus 131 point rho, sorry, 131.1, and this gives you the, if you incorporate rho of oil, that is density of oil, then you can have a API gravity. What is the difference between the normal gravity and API gravity? Basically, if you see the density of oil of each components, oil is a multi-component mixture. So each components, if you take like hexane, heptane, octane. So heptane and octane, if you take two components, they have hardly any difference between their density. So you cannot differentiate these two based on the density when you design it. When you design any column or some equipments to handle this hydrocarbon. So API gravity will magnify, if you say oil is lighter than water, that's why it is float. Hydrocarbon oil I am talking. So let's say any oil, it is 0.9 specific gravity. If you incorporate in the equation of API gravity, then it will be more than, means 2 decimal, right? Means double digit figure you can have. So API gravity greater than 31, you can say it is a light oil. Or API gravity less than 10, right? It is known as a heavy oil, extra heavy oil. So by knowing the API gravity now, you can designate the oil whether it is a light oil or it is a heavy oil. Okay. Next, let us discuss the experimental setup and how we design the reactor. We work many times, we do the research, but we do not follow the design criteria and all. Simply we see the literature and fabricate the setup and do the experiments. But for any sort of reactor, we have a design criteria. So here, based on L by D ratio, so residence times of the reactant and products is very, very important. So L by D ratio, we basically selected based on the various demerits and merits of this LD range. So if LD is 0.5, then restricted flow. If LD is 0.5, then restricted flow and restricted recirculation within this reactor. If LD is greater than 1.5, then increases the path of recirculation. If LD is greater than 2, then several disadvantages we can have. At least 2 impellers are required for good fluid motion. Thus L by D ratio we selected 1.2 to 1.5 here, right? Now what are the reactor arrangements here we made? So there are thermal pyrolysis, first of all, without catalyst we selected. Then 3 type of catalyst we basically recommended here. One is A type in vapor phase, B type then liquid phase, and C type both the phases. So this is the dimension. You can see the reactor 112 millimeter and 135, it's a height, right? So you can make the make your own this ratio L by D ratio, right, from this dimension. So thermal pyrolysis for this reactor arrangements, if you see here, this is in the purely polyethylene is there is no catalyst. Here you can see polyethylene is there, no catalyst in the liquid phase here, but catalyst bed is in the vapor phase. That's why it is A type. We have said catalytic, but in this is A type. A type means catalyst is there in the vapor phase. Then third one, it is B type. That catalyst is now mixed with the, you know, polyethylene or polypropylene or polystyrene. Here polyethylene with reference to polyethylene I have shown, but it is valid for polypropylene and polystyrene as well. So it was mixed with catalyst, and then reaction was performed. Then C type means catalyst was mixed with polyethylene in the liquid phase at the bottom of the reactor with the feed, and then same amount it was placed in the, vapor phase. So this is multi-phase, also it is called known as a multi-phase liquid and vapor phase or multi-phase reaction. So here, this is the reactor setup. Now I would like to tell you whether it is A type, B type, or C type. This reactor was placed here within a, this furnace, and it's a vertical furnace, and then nitrogen was purged, right, and removed from the oxygen was removed from the, reactor, and then the reactor was heated at varying heating rate. So what was the heating rate? Around 12 degrees Celsius per minute. And there are various heating rate will give you various heating, product distribution. So it was a 12 degree per Celsius per minute, and you can say it is a slow heating rate. And fast heating rate, when more than 15 degree per Celsius per minute it is adopted, we say fast heating rate. In some literature it is given 20 degrees Celsius per minute. So reactor was heated, and then product was obtained, and time was, 30 minutes. You might ask why 30 minutes? Because what we observe, we perform the experiment for each 10 degree Celsius increase in temperature. We analyze the product, and we observe that after 30 minutes, when the experiment was from up to for 30 minutes, no more product was obtained even after 40 minutes. So 30 minutes highest yield was obtained. When we perform experiments in another setup and arrangements for 40 minutes, taking a fresh sample, we observe there is no change in yield. So that's why we stop further doing the experiment with time, the reaction temperature we fix for 30 minutes, right? And the product which was obtained due to the reaction will come out as a vapor, either condensable vapor as well as non-condensable gas. So solid residue will remain, that as a will be collected as a solid residue bottom, and liquid will be collected here. Two conical flasks, they are arranged in series. So first conical flask, whatever the condensable gas will be trapped here. If there are still some condensable gas which moves out, go out from the first conical flux, they will be collected here in the second conical flux. So there is a no chance of loss of, condensable vapor as a liquid hydrocarbon, and non-condensable gas will be, it was not analyzed, but it was trapped, and we have seen that it has a fuel value. It burns with a flame, blue flame we observed when it was burned. So it has a calorific value and fuel value, because it is a basically mixture of methane, ethane, propane, butane of lower hydrocarbons. So this is the reactor arrangements. Now I would like to discuss result and discussion part, very interesting part. What are the products obtained from the pyrolysis of polyethylene, polypropylene and polystyrene using thermal pyrolysis process? And second part is same using catalytic pyrolysis. So catalytic pyrolysis using ZSM and using fly ash, both we have discussed in two different subpart. Now polyethylene, if you look into this table, what we observe during our research, that with the increase in temperature, if you keep on increasing the temperature in this direction, 50 degree, 500 degrees Celsius, 600, 700 and 800 degrees Celsius, and weight of sample for all this was 50 gram, right, of plastic waste, right, polyethylene. and that 800 yield was very high but waxy. Yield is higher than 700, 600 and 500, but waxy in nature, solidifies at room temperature. Gas was, you know, you can see there is a little bit fluctuation, 18, 20, then 16, and again 18.4. You can say why it is 18.4 again, because of the repolymerization at thermal pyrolysis, that more amount of solid we absorb at very high temperature, right? And why waxy after 700 degrees Celsius, that is at 800 degrees Celsius? Because if the temperature is high, because heating rate is fixed, at high temperature, residence time, the molecules which was formed from the thermal pyrolysis of plastic, and the larger molecular weight hydrocarbon did not get sufficient time to be there in the reactor and escaped due to the high temperature, as a rate of vaporization was high rather than a further conversion. So it escaped from the reactor, and which was appeared as a liquid yield, and finally it was waxy because of the higher molecular hydrocarbon of paraffin. Higher paraffins are basically waxy. C greater than 30, as it becomes semi-solid and waxy in nature, right? So if you see that product of 700, it's a good quality, means quality in the sense not waxy, non-waxy. So here, that's why 700 degrees Celsius was selected as a optimum temperature for thermal pyrolysis of polyethylene, and 700 degrees Celsius, this physicochemical properties of the pyrolysis oil obtained at 700 is reported here. Flash point 27 degrees Celsius, 32 degrees Celsius fire point, quite low. Okay, carbon residue very low, density of oil this, and API gravity you can see 52.65. That from this you can say it is a light oil, because I have said API gravity greater than 31.3 or 31, it is basically a light oil. So it is a light oil basically, and calorific value is also good. You can see what we know, that calorific value of gasoline in the range of 1500 to it comes in the range of 11,000. So here it's very close to gasoline, but it is a thermal pyrolysis. Maybe because of the L by D ratio we maintain properly, and this is a solid ratio. Not, it is not catalyst, solid residue left over after pyrolysis, and this is pyrolysis oil at 700 degrees Celsius. Similarly, polypropylene, if you look into this, 800 again, quite high, higher than polyethylene. So we got here liquid oil, that is 86%, but problem is at 700 degrees Celsius again it is waxy. I have discussed the reason why, without further conversion, because of the high temperature, vaporization rate is higher, so it goes into the vapor phase and then to the condenser without further conversion. However, lower temperature 700, 600 and 800 degree, they get sufficient time for the further conversion. So that's why we get little higher of liquid oil in comparison to 500 and 600, but liquid in nature. They are not the oil is not waxy at 700. Similarly 600 and 500. That means lower paraffins are higher amount in this three type of oil. Okay, but if you see the BTX analysis, that then thermal pyrolysis will always is giving low BTX content in comparison to catalytic pyrolysis, that I shall discuss in the catalytic pyrolysis section with thermal pyrolysis in comparison. So 700 again is the optimum temperature. You can see from the previous one, this oil and this polypropylene, the color wise you can see there is a difference, maybe due to the presence of different types of aromatics compound. And here flash point and fire point again it is low, and calorific value of course little lower than this previous one polyethylene what we obtained, that due to the the various types of hydrocarbon which are present in the oil. Similarly, polystyrene, that thermocol, we took basically thermocol as a raw material here, and again for temperature, different temperatures we perform the pyrolysis. 800 again waxy, high but waxy in nature, 91% but waxy, but here it was 96% but non waxy in nature, right? So this reason is I'm not going to again discuss. So 96 liquid, as it is liquid in nature, so we took it as a optimum temperature, 700, right? And this oil of 700 analyzed to get the know the physicochemical properties. Flash and fire point, again it is low, and low in the sense gasoline, 35 to 40 range, this flash point. Now if you compare with this gasoline fuel, then of course it comes in the range of gasoline fuel, again low flash point. So there is no problem of startup in the engine or combustion. Carbon residue, again 0.86, low percentage. Density, API gravity, it shows that it is a light in nature. But color, you can see little more brownish because of the styrene monomer. What we have observed, the pyrolysis of plastic waste, thermal pyrolysis of polystyrene, mostly it gives the styrene monomer. Monomer it remains in the product oil. That's why its color, it becomes more brown in comparison to oil obtained through pyrolysis of polypropylene, means dark brown, and that is the light brown polyethylene, and you can see polypropylene, it's almost clear, right? Water like, you can see color. So catalytic pyrolysis, if you see the catalytic pyrolysis of ZSM5 first. So before we go for the catalytic pyrolysis, what we did, the 50 gram of feed we took total, and 50 gram feed, feed to catalyst ratio, what we maintain, 20:1, 30:1, and 10:1. 10 is to first, then 20:1, 30:1 for each polyethylene. Then what we observe, that liquid yield was 58% as the highest percentage here in the catalytic pyrolysis for 20:1. Here also 81% and also 86% for polystyrene. So as the liquid yield was highest for 20:1, and we took it as a optimum feed to catalyst ratio for catalytic pyrolysis using ZSM5. Okay, all three comparison I have shown here. If you compare with the thermal, you can see that gaseous percentage is increased, and we know naturally the gas is higher, gas obtained higher in case of catalytic pyrolysis in comparison to thermal. These are the equations which are used to find out yield, liquid yield, gaseous yield, and solid yield. A very simple technique. Liquid, we can weight it, simply weighing balance, amount of liquid yield obtained. Then gas, we do not measure basically. Solid weight we measure. So we combine liquid and gas, liquid and solid, and total mass of weight, feed weight is known to you. So from this we compute the gas. So gas total minus liquid and solid, if you total subtract, then you can find out what is the gas escape. So now all experiments, what I am means results I am reporting here for 20:1 feed to catalyst ratio, as it was giving the highest amount of yield. Now here qualitative and quantitative both I shall discuss in this slide. So feed is polyethylene, right? And if you look into the first table here, what is observed? Thermal pyrolysis, catalytic A, catalytic B, and catalytic C. Catalytic A means vapor, catalytic B is liquid, catalytic C is multiphase. Now, if you compare liquid, catalytic C, you see quantities, sorry, catalytic B here, quantity is lowest amount. Thermal, it is, catalytic, if you compare with the thermal here, and catalytic B means liquid phase, and this is purely, thermal pyrolysis. So this is this has gone down. If you compare purely, what we do, you mix with the feed and then do the catalytic pyrolysis, and gas has increased tremendously. But if you compare this with multi-phase, in both the phase, catalyst in vapor phase and liquid phase, both drastically gone down liquid quantity. And here what has happened, gas has become more than the liquid. That means, here two-stage catalytic pyrolysis is taking place in the multi-phase. Catalyst, when it was associated with the liquid phase with the plastic, it was giving product like B type means liquid type, I have already said. And then when the liquid which is after pyrolysis, which go to the vapor phase, and due to the catalyst in the vapor phase, further cracking of the smaller fragments will take place. That's why the catalytic pyrolysis multi-phase type giving lower liquid yield, and this liquid is being converted to gaseous products. And at the same time, liquid which is obtained through this type of catalytic pyrolysis, I am telling you, it is rich in aromatics and better quality. I am talking of aromatics: benzene, toluene, ethyl benzene, xylene. Suppose there is a hexane in the liquid products which is coming from the bottom of the reactor of this A type arrangement. So C is nothing but combination of vapor A and B, combination of both these vapor phase and liquid phase combination. So that's why there is a more aromatization and further conversion of alkane to smaller larger chain to the smaller chain. That's why you are getting more gas and the liquid product with more aromatics content, BTEX. So if you see this C type pyrolysis, right here, all these constituents, benzene, toluene, ethyl benzene, xylene, and total BTX content 39%. Now let us compare with this thermal pyrolysis. BTX content only 10%. Though liquid yield was high, here 68%, right? But the BTX content is very low here, okay, for purely thermal. And when C type means multi-phase in situ aromatization we are doing, okay, then you are getting more aromatics here. And among these means total aromatics, what is the percentage of benzene? 15%, highest amount. Then 2.6, 17.03, 4.42. So benzene, as such not considered as a fuel component, because if you see the commercial diesel, gasoline, kerosene and gasoline, all these three fuel we have analyzed and seen, we have observed that less than 1% uh, carbon residue is sorry, benzene is there. So benzene must be there, remember, less than 1% in the fuel, whether it is a diesel or kerosene or gasoline, but here it is 15%. So how to use this fuel to complete this total amount of oil which is obtained as a for IC engines, whether it is a kerosene as a kerosene or diesel, you cannot recommend because benzene is very high. So what to do? The best way is to remove this benzene from the oil, separate the benzene from the oil, and then you recommend it for diesel engine after separation. Okay. Now if you compare with other processes also, then you can see the change in toluene content, that all are have increased here. So toluene, xylene, ethyl benzene, also have increased. If you compare, so B type, I have said it is a liquid phase reaction. It's generally we perform. They mix the catalyst with the feed and then do the pyrolysis, get the product. So if you compare with this multi-phase, there is a enhancement. Even B type means liquid phase and multi-phase. If you compare 9% increase in BTEX, in the oil, in the total oil. Now, one more thing I would like to share with you that total BTEX content in the gasoline 36.45%. Here we are 39.45. So we can remove this one and then we can recommend it as a gasoline as well. Okay. Next is polypropylene. So polypropylene also same observation what we found here. Thermal pyrolysis 80%, right? Here catalytic pyrolysis giving 82%. But you know catalytic pyrolysis give more gas, right? Here liquid is low because solid was very high. Liquid was low because solid content was low here, and the problem occurs when you know you go for catalytic pyrolysis, but you do not look into the composition. Composition is very important. Then reactor arrangements you have to change. So you see B type 81%, here 82%. But why is the change? Then gas has increased because solid residue has gone down. That's why liquid is little bit high and gas has also increased. So what benefit we are getting in multi-phase, that solid content, solid residue has gone down here, right? So and we are getting more gas and also liquid of good quality. Quality, why in quality is I am talking good quality of oil, because if you say here BTX content is 53.09% for C type, that is multi-phase pyrolysis, and if you compare with the this thermal pyrolysis, this 30.9, here 53.09, so 28%, 23% enhancement. But catalytic pyrolysis, among all these three catalytic pyrolysis, again there is a increase in the though not high, but still we are getting little increment in weight percent of BTEX. So already the reason for such change I have discussed, and this is the reaction alkane to carbonium ion due to the pyrolysis, then cyclization, dehydrogenation will give you aromatic, and then alkane or alkene, light alkane or light alkene due to the beta session. Already I have discussed this, how we are getting this different types of aromatics. Similarly, polystyrene, it gives 96% of yield, liquid yield here, and if you compare with the C-type multiphase, 83%. Though liquid yield is low, but quality-wise it is good, because you see a 26%, 86 highest amount of aromatics BTEX is found in comparison to thermal pyrolysis. For it was 96%, but BTX is low, only 13.58, just double. If you do multi-phase pyrolysis, liquid and vapor phase, then 26.86%, it becomes double. And liquid is, I told you, it is low because it has been converted to gas. Gas means valuable fuel gas, and that can be recommended for as a fuel. And next. Before I go to the catalytic pyrolysis, I'd like to highlight one thing. The gaseous fuel which are getting from the catalytic pyrolysis of C-type, it's the highest high amount, very high amount. And that gas can be used after trapping either as a fuel, store it and use it as a fuel, or this gas can be used as a fuel for the combustion, and the heat will be generated, which will be generated, that can be used for pyrolysis of this plastic waste. So this process will be sustainable and self-sustained, you can say, this technology. No need of source of external heat. The fuel gas which you are getting, you burn it and use it in the system, and to for the thermal or sorry, here we are talking multi-phase pyrolysis. It is the best process, so recommend it for multi-phase pyrolysis of plastic waste. Okay, so self-sustained process. Fly ash catalyst. If you look into this fly ash, what we did, I already have told you, natural catalyst, Fa600, Fa700, based on the temperature range, and Fa800, 900. Just look at the surface of the catalyst carefully. Here, same magnification, the catalyst covered some organic mass, right? Unburned carbon. So to remove unburned carbon and all from natural catalyst, we calcined it 600. So there is no unburned carbon now, that this surface is exposed. But pores are not visible. The pores which are there on the surface of the catalyst, they are not visible. More the pore will be opened up, more will be the active surface area, right? Now, if you look into this, uh, what we have observed, I will show you the BT as well as semidax information. More the temperature of calcination, more silica alumina, because of the exposure of more surface and more pore volume and more surface area. But 800, this way, with the increase in temperature, gives highest surface area and highest silica to alumina ratio. However, at 900 you can see thus the structure or surface morphology, where we can see that there is a collapsing of pores at high temperature. So 900 degrees Celsius, if it is calcined, that pores get collapsed, and due to the pore collapsing, the surface area becomes low, and the silica alumina also ratio it get down, right? So what conclusion we can draw from this? The 800 degrees Celsius is the optimum temperature of calcination, at which surface area is high, as well as there is no pore collapsing, though pores are not visible, but pores are there. Okay, and that's why the means pore volume is high, and silica alumina ratio is high. So let's see this analysis: surface area, pore volume, average particle size, silica alumina ratio. So let's come to this 800 and then uh, you know 900 comparison, in comparison to 600 and FAN natural catalyst. Just four, not do not take all. So for ease of convenience, for a better comparison, compare this. So 224 2.25 pore volume and surface area 1.74 here. Now if you go to compare with this 600, little higher, pore volume is also higher, particle size also gone down, and then silica alumina ratio is also increasing. Now come to this 800, that is the optimum temperature, highest surface area 310.40, and pore volume is also highest. Not I'd not say highest, means very high pore volume, right? And here what you can see, average particle size is also low, and then silica alumina ratio is 16.03 highest. Because of the high surface area, you are getting highest silica alumina ratio here, in comparison to this 900, because of the pore collapse. Okay, what we observe, 5.73 is the surface area and 1.43 is the silica alumina ratio. Now if you do the study of pyrolysis, similar arrangements for all three catalysts, five type of catalyst, four calcination temperature and one uncalcined natural catalyst. So A, B, C type. So if you compare four catalyst for 800 and C type, four catalyst of different temperature, calcination temperature and C type. So here it is C type. If you take this one, this one C type, and this one C type, here also we are talking of multi-phase is best one. So 0.19 is the benzene here, and here you can see 3.05 and 6.39 is the highest benzene content here, and also you can see 7.95 is the toluene highest percentage, 5.57 is the ethyl benzene also highest, and 2.21 little increment, but you can see that 800 in comparison to this catalyst, if you compare this value and this value C type with thermal pyrolysis, okay, you can see always this is the highest amount, 800 calcined and C type, right? Calcined at 800 degrees Celsius and C type. Now total BTX content is 22.11 percentage here. Here you can see 10.92 percentage in the thermal pyrolysis, and I have shown already for polyethylene. So although not very close to ZSM5, but it is giving higher aromatic content of BTX in comparison to thermal pyrolysis, and 900 giving lower because very low here, 900 giving 9.28, very close to thermal pyrolysis. Not as such, no increase in BTX content was found. Again, in every cases I have shown here the references diesel, kerosene, gasoline for better understanding what is the BTX content in those three types of fuel, standard fuel, and what BTX we are getting in our process. Similarly, polypropylene, if you see 10.34% benzene, C type 800 here, and C type highest again means to, if you sum up, then 43.43. But polypropylene giving xylene is very high amount, and then benzene. So total amount is 43.43. Of course, this pure thermal pyrolysis was giving 30.90, but in comparison to this, we are getting 10 weight percent, 13 weight percent more BTX here. And also, if you compare 13.57 here thermal and catalytic giving 20.93%, which is again 17%, around 16-17% more in 800. But if you compare any other with this, of course, any sort of catalytic pyrolysis using rest of the catalyst, then you can say that it is lower than F800 of C type pyrolysis. Now, what we did, we also performed the catalyst stability and regeneration. It is a very important part. We did first run, second run, and third run. Then we stop, and we observe the change in yield after first run without regeneration. So after using fresh, this is a fresh catalyst. You can see this is used catalyst, right? After let's say first run and then regenerated. How it was regenerated? The catalyst was calcined for 500 at a for 5 hours at a temperature of 550 degrees Celsius for and then what happened? All the carbonaceous part was removed, and then we got this type of white is regenerated catalyst, very close to original catalyst. And similarly, ZSM5 here you can see regenerated here catalyst, and it is used catalyst, right? So all these three type of catalyst what you have seen, they are same images. If you see the BET surface analysis area, surface analysis of used fresh and regenerated catalyst. Let's see the surface area. So F800 catalyst, 310 was initially fresh catalyst, and regenerated 305, very close, but used one has gone down 215, right? So similarly, ZSM5 400, used one 302 gone down. Again, after regeneration, you can see that almost 300, 400 and 390, only 10 unit, 10 meter square per gram is difference. And still there is a coke deposition, and which has blocked the pores. That's why we got this type of observation. And if you see the same images, this is fresh and regenerated, very close, and used one, though we cannot differentiate, but it ZSM5 little bit we can make a comparison, regenerated and fresh and regenerated, and this one is used one, where carbon deposition is clearly seen and the particles are not visible here because of the deposition of coke. After experiment, what we observe, using this regenerated catalyst. The fast run, this is fast run A type and C type. Let us compare the C type, right? The liquid one, C type. This is C type, and C type here, and C type also. What are the difference here? First run, second run, third run, and fourth run for F800. Sorry, fourth run, and then after fourth run it was regenerated. So what is the change you can find? First run, C type, and here C type, there is a change. Then it is decreasing. Once we regenerate the catalyst and reuse this regenerated catalyst and fresh catalyst, almost there is hardly any difference. Same type of liquid we observe. Similarly, in BTX content, fresh and regenerated very close. So ZSM5 also, if you look into it, 46% we are getting liquid yield here, and regenerated giving 46, same amount. But if you look into after third run, without regeneration, it's gone down 43.472. Similarly, for the BTX content, here you can see almost same, regenerated and the fresh one. But in between, if you say, let's say third run, there is a lower in BTX content. So conclusion, I would like to conclude the main observation or outcomes of this process using these three plastic waste. So maximum yield and aromatic content, what we observe for thermal pyrolysis: polyethylene 68%, and this is aromatic content 10.7275. For polypropylene 86% liquid yield, and this is BTX content. And polystyrene for 96% and 13.57%. Okay, this is aromatic content. Similarly, maximum BTX content for catalytic pyrolysis using multiphase. I am talking of multiphase only, and FA800 catalyst. Okay, which is around 22.11% for polyethylene, 43.43% polypropylene, and 20.93%. This is for polystyrene. Whereas ZSM5 catalyst produce 39% for polyethylene, 53% for polypropylene, and 28% for polystyrene. So we can compare here among these two catalysts as well. The test result for catalytic stability indicates that commercial ZSM5 and synthesized Fa800 catalyst is stable up to third run, and there is slight change in liquid yield and BTX content. Regenerated catalyst showed similar result as that of fresh catalyst. So regeneration is must for to make the process economically viable and cheaper. Physicochemical properties of pyrolysis oil shows that it can be used as alternative fuel, as a source of valuable chemicals such as benzene, and as a source of valuable chemicals, as I've already said at the beginning, benzene, toluene, ethyl benzene, and xylene. So these are my ongoing projects. I have not shown here the publication, that there's a long list of publication. These are ongoing projects and completed projects. And we have got a best paper award in ChemCon 2016 for this work, product characterization and fuel properties of renewable petrochemicals from pyrolysis of waste plastic polystyrene. These are latest publication 2021 and up to 2019. Major on pyrolysis only. So this is my research groups of PhD awarded and ongoing PhD students. These two means among this 7, they will 2 will submit get degree soon, waiting for oral examination. These are my MTech students, and there are many UG stream project, exploratory projects. Because of the COVID, they are working from home, and with this this last slides of my research groups, I'd like to stop it here today. if you have any questions, you are welcome. Thank you everyone for your attention and giving me time to discuss my research on this pyrolysis of plastic waste to have energy. Thank you again.
Thank you, Professor Hiralal. Now I think the participants, if you have any questions, you can ask, sir. The participants
Thank
have
you,
any
ma'am. Yeah,
questions?
yeah. Any sort of questions you have from this overall presentations, you are welcome.
So I think it was very clear, maybe, or two extremes. Your
Thank you,
presentation,
ma'am.
but it was very. I like the presentation because I also work in the same
Right,
field,
right,
so it was very interesting. You gave a very detailed description of the experimental setup, how the characterization has to be done, and many of the young faculty who are here can take it up because it is there is so much more to do, especially
right,
in the development of the catalyst. So if
right.
they're interested, I think they can also contact you and you can
Sure,
give
sure, ma'am.
them advice as to how they should take it forward. So
Right.
I thank you, sir, for accepting to give this talk and having spent so much of time and giving us such a good and extensive details about the work that you have done. I still want to ask if anybody has any
Right,
questions,
right, ma'am.
kindly ask them. And also, feedback forms I think will be there. Kindly
Sure.
fill the feedback forms and send it to us. Thank you, sir. Thank you
Thank
once
you,
again.
ma'am. Thank you. I would like to again thank you for giving me this opportunity, ma'am. I hope we will again sometime meet soon to discuss, on such, means burning topic, right? Thank you, ma'am. Thank you, everyone, for your, kind attention. Thank you.
Thank you, sir. Thank you very
Thank
much,
you.
sir.
I hope I may leave now, ma'am.
Yes, you are welcome, sir.
Thank you, ma'am. Thank you so much.
Thank you.